Last talk of the day, we have a presentation by John Micco and Atif Memon, going to talk about some research they've done at Google on Flaky Tests. So take it away.
Okay. My name is John Micco, as he said, and I'm a manager managing internal testing, continuous integration at Google. This talk is mostly about some work that we collaborated with Atif Memon. He came and worked on sabbatical with us for about 6 months, and we sent him into our data, and he came back with some interesting stuff. And so here's the stuff. Anyway, Atif, if you want to introduce a little bit yourself, too?
Sure. I'm Atif Memon. I'm from the University of Maryland in College Park, and I spent the first half of this year in John's group during my sabbatical.
Yeah. So let me talk a little bit. I want to set up the problem a little bit, and then let Atif talk about some of the stuff that he's found from our data. Atif thought I was really great managing his project because basically I was too busy to help him. And I gave him terabytes of data and said, go find what you can find in there and let me know what's interesting. And he did, so it was cool. But one of the things we're going to focus on a little bit is about flaky tests. A lot of people don't think it's an important problem. I even was talking to a grad student who sent out a paper, a PhD thesis on flaky tests, and was told by peer reviewers that it's not an important problem. Well, I'm here to sort of dispel that rumor and to say flakiness is a problem for us. We define it as a test that passes and fails when run on the same exact code. So if you can take the same code and run it twice, or run it n times, and if you observe a different result, then we call that a flaky test. One of the most startling observations, which was just sitting in our data waiting to be discovered, was that 84% of the time when a test was passing, and then it starts failing, 84% of the time that indicates a flake and not something that somebody broke. That's huge, and that's across all of our test corpus. Almost 16% of all of our 3.5 million tests have some level of flakiness. They've been observed to flake at least once. Flaky failures frequently block and delay releases for us, pushing out to the web. People have to investigate to figure out whether it's a real failure or not, or run it again, or wait, or whatever. And we spend somewhere between about 2 and 16% of our continuous integration compute resources rerunning flaky tests. And this little box diagram that you see at the bottom that's very busy and looks like almost Christmas time, maybe it is almost Christmas time, you can see here that this little box is the test history for a single test that's flaky. And any person looking at that can say, yeah, that's a flaky test. It probably never broke for real, at least not in the window that we're seeing here. Maybe there's like 3 in a row right up in the top row. Could be a real failure, I don't know. Probably more likely a flake. And so this is just, we start monitoring this, and this is how much of our compute resource pool we spend on rerunning flaky tests. It might not seem like a lot. Oh, it's only 5%. If you knew the size of our pool, it's pretty expensive. Let's just put it that way. And what are the things that cause tests to be flaky? Well, we haven't done a good analysis yet. This is an area we'd like to do some more research in. But it's all the things you would expect, race conditions, waiting for resources, multi-threaded testing, environment issues. Either it's the code under test or it's the test case. I mean, we really don't have a good breakdown yet, and we'd like to have good data about the root causes of all the flakiness. That would help us sort of characterize things better. So it's an area we're still trying to figure out from our data. There we go. What we also see is that when we run tests, we run our 3.5 million tests, we do it continuously. We're seeing about a 1.5% of the tests that we start running end up resulting in a flaky failure. That's a pretty big number, and like I said, it continually blocks our releases. And also, if you imagine, in order to ship a project like Gmail has 30,000 tests that they care about. So if you have 30,000 tests and 1.5% of them are going to flaky fail when you run them, are you ever going to be able to ship? Well, yeah, you can, but it's kind of a little bit of a pain to do it. And despite we've made a large and concerted effort to fix flakiness, to go after the developers and say, damn it, you should fix the test and make it less flaky. We tolerate a certain level of flakiness across the board. we still observe that the insertion rate is about the same as the fix rate. As developers write new code. So we really haven't been able to make much progress in reducing the total number. And really, CI systems all have to deal with a certain level of flakiness in the tests. And we really want to try and minimize the cost to developers and to releases and to velocity of having these flaky tests in our continuous integration system, because they're not what the continuous integration system is all about. We're trying to find developers actually breaking the stuff, right? So. Again, I've used the number a few times. Every time a developer at Google submits a change, we look at what he changed, and we do a reverse dependency map through our build system and find all of the tests that depend transitively on the thing that was changed, and we schedule them to run. And we do that as fast as we can and as frequently as we can. Most tests have two distinct flag combinations that they run with on average, like say opt and fast build. So some optimized build and some debug build, we run them both. And then we record the pass-fail result of each and every test in the database. And we uniquely identify those by the test that was run, the flags that were used, and the change that was submitted by some developer. And we have 2 years of test history of all of these test results, pass-fail. And every night, every time there was a down transition, a transition from pass to fail, we sick our deflaker on it, and it runs the test 10 times and says, did it ever observe a pass? If it did, then that test is marked flaky. And we keep a database of all the flaky tests. And we're starting to do a few things that are a little better than that, but that's something for the future. And we're just really touching on the very beginning of analyzing those terabytes and terabytes of data. But they allow us to do a lot of good hypothesis and to see if it's borne out by the data. Is it that tests fail more frequently when the systems are loaded? Is the test, any kind of thing that you can think of, you can look at our data set and you can answer it without having to run any tests, without having to do anything much about it. You can also get the correlations between changes that were submitted by developers and failures that occurred, right? So you can say, oh, you know that this CL caused this test to break. And so you can start answering questions about, well, what are the commonalities between changes that cause tests to break? And that's some of the research work that Atif will talk about in his half of the talk. It's really pretty cool what he's discovered on some of the data. So I want to talk a little bit about how our continuous integration system works. We have our happy developer over there. He submits some code. I'm going to make Gmail better today. I'm picking on Gmail. I hope nobody's here from Gmail. And he submits a change. That change goes in. We say, hey, what tests should be run on that change? What did he change? And what tests depend on the thing he changed? Let's schedule all of those. So we send them to our test scheduler. We batch them up. We batch them into groups. We run on a massively parallel backend, but it's like a two-stage system. I don't want to even go into the details. It's very complex. But first, we have to batch up the tests that we're going to run together. We pick usually between 400 and a couple thousand tests that we're going to run together. And we run them into the massively parallel backend and get the results. So we build, we run the tests, and we record the tests back in the database. Along the way, there's a certain amount of infrastructure failure when you're running, millions of tests. Every now and again, something goes, oops, and a machine crashes or Borg evicts a job or whatever it is, and the test doesn't get completed. And we reschedule those until we get a result, pass or fail. So we guarantee that every time, as frequently as we can, we get a positive or negative pass or fail result for every change that was submitted. Now, we skip over some of the changes when we don't have enough resource to run them all, because we don't. We basically end up running less than half of the triggers, the times when we think the test should be run, but we always schedule it at the next time when we have resources. So I know that's a little confusing, probably a little more information than you needed, but we actually can't run every test at every affecting change because there's just too much work to do. But we actually give back to developers a result after submission supposed to be within 2 hours is our SLO, trying to give results to a developer that their submission passed or failed all the tests that were affected by it. We don't always meet that SLO, I'll be honest. Some people here from internal could probably call me on that. But we're doing our best, and generally it's within 3. We also have a tool that tracks, as I said, all of the flaky tests. The names of the tests have been blacked out to protect the innocent or the guilty, as the case may be here. But this particular display aggregates all of the times, and we keep track of the stack trace and all the information about the tests that Flaky failed. And we try and later on determine if a new thing that we're seeing matches an old Flaky test, it's the same stack trace, then we assume it's a flake. But if it doesn't match the same test and the same stack trace, it could be a new failure of a Flaky test, which is a little bit different, harder to discover. But we keep this database so that we know we can get developers looking at the tests that are the most flaky. We can tell, we use it as a indication in our UI. Hey, this test failed, but we're pretty sure it's a flake. You don't have to worry about it. So you don't have to investigate as carefully those things. And we're trying to get a lot better. Murat, is Murat here? He must have left. But he, one of the guys who was here earlier in the day, Murat in England, London, he's running the group that runs this infrastructure that records all the Flaky tests. And they have some great plans for the future of how they're going to make this better. And using some of the techniques that we're going to talk about, or that Atif will talk about in his half of the test. So without further ado, let Atif show you some of the interesting things that he found in our data.
All right. I need to know how to...
Just the green. That's it. Okay. It's pretty simple.
Cool. All right. Okay, so as I mentioned, I was on sabbatical at TAP, and it's an amazing group to be in. If you are looking for a sabbatical, you should contact John. It was amazing for a couple of reasons. One is that the TAP team is amazing, so they're very helpful and very friendly folks. Second reason is I have access to all this data, right? I have terabytes of data, all the test results for the last 2 years, all the code that corresponded with all the results, test case code. All right, so I'm looking at all this, I'm staring at this data for 6 months and analyzing it. So that was good. The analysis and the results, I think, in my opinion, I think they have led us to almost a breakthrough in how Google can handle flakes in the future, right? We are at a point where we could be looking at test results of a single test case and look at it and say, oh, that's a flake. We don't even need to rerun it 10 times, right? Like how we do right now. And I think that's, if we start incorporating much of the things that we have found, we should be able to do much better than we are doing now. As my 6-year-old daughter, she's the one who's the artist on these pictures. That's her interpretation of what we're trying to do. The scientist on the left, who looks a lot like a princess, she is saying that I am 97% confident that this result is flaky, and this other person is saying, how can you tell without rerunning it? Because real tests don't behave like that. And John kind of said this. If you look at this test result, and those Fs are the failures, and the green ones obviously are the passes, and the other ones, the ones with the dashes and other things, are results that we could not obtain for various reasons. One of them that we didn't have resources to run at every change. So if you look at this result, a test went from pass to fail, fail to pass so many times, and real tests just don't behave like that. All right? It's not that developers break tests and then they fix them after an hour, after 2 hours they break them again. Right? They remain pretty consistent. So you will find that there are lots of failures, and then most of the remaining ones are passes. So by looking at it, you can tell. All right. So I want to thank my daughter for drawing that. So thanks, Privi. All right. So what we want to do with this result is we want to take our flaky test infrastructure. It's not that the infrastructure is flaky, the tests are flaky. We want to improve it, right? And how are we going to improve it? We want to identify flaky tests without rerunning them in 3 ways. One is we're going to follow our intuition. And one of the intuitions that John and I had was you can look at simple signals of pass and fail patterns, right? Like how we just looked at those reds and greens to indicate flakiness, right? Let's try to formalize that. The other one is let's try to find features of flakes. What makes a test flaky, right? Are there signals that we can derive from all this data that tell us that, oh yeah, flaky tests behave in a certain way, all right? They have certain characteristics, not the pass and fail only, but other things, all right? And whatever our first models have shown that we are right a lot of times. So we've been able to classify 90% of the flakes correctly. Then we have the opposite problem. If we can identify flakes, we should also be able to identify real failures. So if you give me a failure or a transition from pass to fail, I should be able to look at it and say, this is a real failure or this is a flake. So how about we identify features of real failures, all right, and then use that to filter out flakes? Because if something is highly correlated with real failures, any deviations are highly likely to be flakes. For example, if one of the results that we saw was a file that has been modified by more than 15 developers in a week's period, all right, is 97% likely to cause a failure, all right? So that's a feature that we can find which is highly correlated with a real failure, right? We can use those kind of things. What do we do with that? First, we want to model flakes and their behavior. So I'm going to show a couple of slides where I'll show you how I formally modeled a flake and its results, and then I'll show you some of the results. I will only give you like a preview of most of the results. We have a couple of papers in the pipeline that will describe more, and you can talk offline about whatever questions you might have. All right, so this is how I'm modeling a test target and a failure. A test target is really a test case for all practical purposes. So that's a test target. That's the name of the target there, top project, some service test. And here is its test history. Now, CLs in Google are code commits, all right? So you're committing code. You're going from the left-hand side. You keep committing code, and you keep running this test case, and you get passes and fails, all right? And I'm going to start modeling this history in terms of negative edges and positive edges. So simply put, you went from a pass to a fail, that's a negative edge. Fail to a pass, that's a positive edge. All right? So here we have 3 edges in the history of this test target. And I'm going to model them as the start CL, which is the commit at which the edge starts, the end CL, where that ended, the length of that, which is like how many commits were in between, and whether it was a positive or negative. Right? So each history, I'm going to model it like this. I have one way of describing my test history. All right, so I took more than 1 million of these edges, all right, and I looked at how TAP, which currently reruns test targets 10 times at night to deflake. I wanted to see which of these edges were real and which ones were not. And it turned out that 84.5% or 85%, close to 85%, were due to flakes. With confidence, we can say that. Okay? The remaining 15% most likely did not include flakes, right? But they may have. Now, if you imagine what this means, whenever you see a pass to fail, right, you send this to, you recognize this as a failure, you send it to somebody to look at this manually, all right? So you have a build cop or you have a developer who's looking at this, and 85% of the time this developer says, oh, that was a flake, throw it away. There are enormous resources that are being wasted because of this, right? And only 15% of the time, this is due to real bugs. Okay, so the takeaway message from this slide is that even though a small percentage of flakes at a given instant, a small percentage of overall results are due to flakes, 1.5 to 2% are tests are flakes. But if you look at over a time period, a flaky test that can go pass to fail very frequently will give you so many edges that it becomes 85%. And that's a much better indicator of the impact of flakes than just saying that there are only 1.5% of our tests that are flaky, all right? Okay, so here's our scientists again. All right, so let's start looking at some of the features of flakes. How can we start to automatically identify flakes, right? So there's a hypothesis that flakes have a larger number of edges per time period, right? So I have 2 tests, test 1 and test 2. Test 1 seems to go from plus to minus many times, like fail to pass and pass to fail. Test 2 does not seem to do that. And over a 5-year period, 5-hour period, all right? So let me start modeling some of this. So I'm going to take all my test cases, all right? And I'm going to partition them based on number of edges that I've seen in their entire history, okay? So for example, test targets that have 21 edges, okay? They are in this vertical bar here, 101 and 816, okay? And then I'm going to see of those test targets, what percentage were flaky and what percentage were not flaky, right? So the test targets that have 21 edges, 60% of those were not flaky, right? But 40% were, okay? As you move in this direction, more and more become flaky. If a test target has 816 edges, it's definitely flaky. Let's fill in the gaps here, and you can start seeing, even though it might not be very clear because of the color, you'll see a lot more blue here, all right? And then the red starts taking over here, all right? So as you increase the number of edges, you are getting more and more flaky, right? So the takeaway message from this is that test targets with more edges in their history are more likely to be flaky. That's a great signal to look at if you're looking at, if you're trying to filter targets based on flakiness, right? Because measuring edges is easy, right? And counting the number of edges over a time period is straightforward. Now, if you notice, there are some blues in here with large number of edges. And when I showed this to some folks at TAP, their comment was that most likely these are flakes, which were not detected by a TAP. All right. Now, let's start to quantify flakes. How can we say that something is more flaky than less flaky, all right? So what I do is, this is a result which is most likely not flaky, all right? And that's a flaky target, right? Test. How do we start to quantify this? Let's start to compute a flakiness score, okay? What we're going to do is we're going to extract these vectors, and I'm representing that simply by using a regular expression there. But what we're saying is start looking for patterns which are a failure, at least one, right, or more, followed by anything which is not a pass, and then a number of passes, and then followed by anything, and then followed by a number of Fs, okay? If I can extract vectors out of this history which fit those patterns, right, and then I fit them into this formula, which I'm not going to disclose, but it takes two parameters. One is the number of vectors that I found in the history of the test target, and what the length of those vectors were, right? If I can do that, I can compute a function for each and every test case. Once I compute this function, I can then correspond that with what TAB believes are real failures or not, flakes or not, because of their 10 times they run their test cases, right? So the top 404, according to my score, were 100% agreed by TAP, that yes, they are definitely all flakes, okay? 991 of my top 1,000 were flakes according to TAP. And then the percentage drops as I go down to, say, 25,000. So of my top 25,000, 23,930 are flakes. So percentage is still pretty good, okay? So I can actually start to quantify flakiness, and I can start to rank all the test targets by their flakiness score. Another thing I can do is, if I can see if a test target's flakiness is increasing or decreasing, right? Let's say somebody changed the code of the test case. I can now start to say that, oh yeah, over this period, the flakiness score went down. Now somebody made a change, flakiness score went up. So we can start figuring out why test targets became flaky, okay? Okay, let's look at something else. Flakes are unlikely to share their histories with others. Imagine this. I have 4 test cases here, right? Test 1 and test 3 have exactly the same pass and fail pattern. And test 2 and test 4 have the same pattern over this 5-hour period. What does this mean? It means that all these test cases are highly unlikely to be flaky, right? Tests don't become flaky in a pattern, right? One bug in the code might cause a bunch of test targets to go from pass to fail, and if they are all sharing that history over a long period, they're highly unlikely to be flaky. Let's explore that hypothesis, and let's see what that means formally. Now I'm going to extract my edges vectors as I did before, all right? And I see that I'm marking those 2 with the blue, and they have identical histories. These 4 have identical histories. They are highly unlikely to be flaky. whereas these two that don't share their history are highly likely to be flaky, right? Let's start plotting this, okay? So this is a somewhat complicated plot, but I'm going to try to explain it a little bit. Both of these are log scales, right? Because as I found out in my sabbatical, everything in TAP is follows some kind of a logarithmic or an exponential scale. So log scales are very easy, hard to visualize, but then they kind of expand the data in the right way. So here, I'm showing you two targets, because this x-axis here is 2, all right? Two targets share their history, okay? I'm going to draw a plot here, draw a dot there, and the number of edges in the history, which is pass to fail, are roughly 20, because on the y-axis, you have roughly 20 there, all right? And that's how we're going to read this. Very little sharing, okay? Because there are only 2 targets that are sharing here. Whereas, if you look at something like this here, 5,000 plus targets, which are, when I say targets, I mean test cases, they share their history, and the edges in this history are 2, okay? There's a lot of sharing, because what? More than 5,000 test cases are sharing their history. Okay, and this is the only history they have. Over the entire period that I looked at, this is the only history they have. On the y-axis, which is x is equal to 0, there's no sharing, okay? Now, if I fill in all this data, and I start coloring them by flakiness as we know it to be from TAP, you see a clean separation. Here, I'm increasing my sharing of history, and most of these targets that I find are green, which means they're not flaky, right? And if I go closer to sharing of 0 or 1, right, there are more flakiness. And if I go in number of edges above 100, then it's almost all red, which means test targets that don't share history with anybody and have large number of edges are almost always flaky. Okay? So if I could compute this history and I could correlate all the histories of all the test targets, I could use it as an amazing signal for whether this target is flaky or not. Right? I keep saying target when it should be really test case. You guys messed me up. They use the term test target for test cases. All right, so that's our result here. Now, the takeaway message is degree of sharing is a signal for flake detection. Okay? If you have questions about this plot, we can talk offline, but I want to get to the next step. All right. So now, let's look at the opposite problem. Okay? Now the scientist is saying, I'm 90% confident that this is a real failure, not flaky. Okay? Now we are not talking about flakes anymore, we are talking about real failures. Okay? How can you tell? Well, because the code and the test artifacts are consistent with a real failure. Okay? Let's look at an example. We used multiple sources of multiple signals. One is a relationship between the code that was changed and the test case that was run as a result of the change. We were going to look at the code modification frequency. We're going to look at the source file type. All right? If you always suspected that C++ was worse than Java, that's true. Changeless authors. Who authored the commit? All right? If you suspected that Joe always broke the build, yes, that happens. And files modified by multiple authors in a short amount of time are more likely to cause breakages. Right? Let's see some of the results. So one is a relationship between the code and the test. Okay? So as we all imagine our code repositories, we can imagine them to be a tree or a DAG, right? Because they depend on each other. So I have a source file that is sitting at the bottom here, and all these other files or packages, they depend on this file for building. So imagine this is like a build tree or build graph, right? So somebody modified this file, and because of this modification, most of the packages that are above it need to be rebuilt, okay? Because they depend on it, directly or indirectly. Okay, so this is my source file that got changed. That's my test
case or test target that needs to be run as a result. How far is it in terms of number of edges? What is the distance between that and that? Okay? If you look at the minimum distance, can somebody count? What's the path that is the shortest? 4, right? Okay, so we're going to call that the min rank, which is the term that Google has used in its documentation. That's a min rank between that node and this node, which is the shortest length of the shortest path. Okay? Is there a relationship between tests that break and the code that gets modified and the distance between them? Okay? So if you look at the min ranks of code, the files that were modified, and the test targets, right? If I plot all of them in Google, I get this plot, right? Now, these are all the min ranks. They start from 1, right? And they go all the way to 41 here, right? That means a piece of code that was modified here and a test target that was run, they were at a minimum number of edges was 41, okay? So that's a pretty deep stack there, right? But if you look at this, most of them tend to be roughly in this area, right? So it's like a wide kind of a graph, and then it goes up quite a bit, right? This is the total population, okay? But if I wanted to look at what happens to only the targets that go in edges, they go from pass to fail or fail to pass, and I plot the probability, most of them tend to lie between 2 and 9, okay? Which means when you modify some code, test targets that are beyond 10 min rank are highly unlikely to break, okay? Most of the closer ones, which are like less than or equal to 10, are more likely to break, okay? Now, how can we use this result? We can use this result as test target edges farther than min rank equal to 10 are highly likely to be flaky, right? If some test target broke somewhere like distance 40 from your code change, that's highly likely to be flake, right? Because now we have a signal for real failures. Okay, let's look at number of times a file was in commit. So when I modify a file, right, I can modify multiple times. Okay, if I modify a file multiple times, I can start counting over a period how many times it got modified, okay? And then when it got modified, it might have caused a breakage, all right? Or it went from pass to fail or fail to pass. I'm going to measure the probability of that happening as the number of times the files get modified increases, all right? So for example, files that got modified 11 times, all right, they were 0.25 likely to cause a breakage, okay? But as this number increases, files that were modified 41 times are 0.75 likely to cause breakages. So file modification frequency is actually a good signal for predicting which test targets might break or not, okay? So this is failures associated with frequently modified code are highly unlikely to be flaky, okay? All right, source file type. We took all the file types that Google had, censored some of the ones that we don't want you to know about, all right? And then we saw which ones contributed more to failures. Now this plot is a bit funny because the black bars are actually all passes, and the light gray ones are all failures, right? So HPP files, they were involved in lots of breakages, right? Only 20% of the time when an HPP file was modified, was it not involved in a breakage, okay? And if you go all the way here, config files were never in a breakage, okay? Where does Java sit? Right here, okay? And where does C++ sit? Right here. Okay, so I'm not saying anything else. But what about how the code is distributed? So we superimposed the curve on top of this, which tells you that how many files did we see in the Google code base, all right? So this is a little known secret, but Java code seems to be the most prevalent in Google, all right? I hope I didn't say this, that I wasn't supposed to say. All right. We still use a lot of Python, C++, all right? And if you look at the frequencies, you can tell that there are some files like HPP, there are very few of them. So they're not going to make a huge difference on our testing cost, even though they might be involved in lots of breakages. But we should be paying careful attention to Java and C++ and those commonly occurring files, right? So failures associated with some kind of files, for example, config files, are highly likely to be flaky because they almost never fail, right? OK, so that's one. OK, authors. This is the interesting one. OK, now it may surprise you that there's no user called ABC at Google, right? But when this user committed code 182 times over the history that I looked at, 59 times that this user broke the build, all right? 31.4%, that's pretty high, all right? Whereas user XYZ was much better, okay? Now this may be for all kinds of reasons. Maybe user ABC is looking at very complex code, right? We don't know. So we're not going to do anything about performance or bonus or stock options. Okay. And there are lots of tools that that modify the code also. For example, product one release is a tool that generates a bunch of things and then it commits code, right? And it committed code 42 times, but it broke the build 39 times, right? I don't know what kind of tool these are, but 92.9%, okay? So if I look at this user, I can say that failures associated with author product one release are highly unlikely to be flaky, right? If I see a breakage by this author, by a code that was modified by this author, I can say that's highly unlikely to be flaky. File modification by multiple authors. This was an astounding result for us. We feel that multiple people should work on code at the same time, okay? But this result shows that I'm going to tell you how to read this plot, but I'm going to show you what the big result is. The big result is when one person is modifying code, they are highly unlikely to break it. When two people modify code at the same time, roughly, the fraction of breakage goes down, okay, in many cases. It's possible because they talk to each other or they send emails and they maybe review each other's code, and that ends up being better written code. But as soon as the number of developers grows beyond 2, it goes up significantly, all right? And then it kind of stays roughly there. But once you get into like 15 developers, when I say users, I mean developers here, then you are most likely to actually cause a breakage, right? So if you have in your company 3 or 4 people modifying code at the same time, just ask them to stop. Okay. Okay. All right. So these are all the signals that we have. There were some signals that were not really related to real failures. For example, number of times a test target was affected was not a strong signal. So we have really good results there. But where do we want to be? We want to be at a point where we say that stop running that test, it's a flake, okay? But you did not even run it even once, right? Without running the test case, all right? But this test has all the elements of a flake, right? What elements does it have? It has these characteristics that we know of that are associated with flakes, right? We want to be there. And we want to be able to predict whether a test is going to be flaky. Now, if I told you that I am going to run an Android test that uses a user interface test harness, right? Uses a bunch of sleeps and wait commands, right? And it's multi-threaded, you'll most likely say, oh, it's most likely going to be a flake, right? Whereas if I say I'm going to run a unit test, which is going to supply a bunch of parameters, it waits for nothing, it's not multi-threaded, it's highly unlikely to be a flake. How about we get all these characteristics, we go through the test cases, we'll go through its code, we analyze the code artifacts, We look at what kind of code is being tested, the execution environment, and come up with a holistic model to be able to predict whether a test is a flake or not, right? Or is it going to be a flake or not? And then maybe we don't have to run it or waste resources on it.
All right, so I have one more quick thing here to say. We did an awesome collaboration with Atif. We learned a lot. He learned a lot. We're publishing papers. It's really cool. But we're still looking to collaborate with other companies, with other researchers who are working on the same kinds of problems that we're working on with flakiness and with predicting breakages. We really want to do, we have lots of data. We have tons of data. If you're interested in piling into data, come and talk to me. And we really do have, the largest test pool, the largest code base around. We've seen a lot of researchers in academia. They study open source projects with tiny code bases and small numbers of changes, and it's really hard to draw good, crisp correlations. With our large data set, we can answer your questions pretty quickly. And we've been working on trying to be better at publishing, and we're publishing a paper with Atif. We're publishing our data set. There's going to be several papers coming out of the work that you just saw. We also, I run a journal review club once a month. We pick an academic paper, we review it, we talk about it. We're always inviting the paper authors to come and to talk, and most often they do, and it's been a good exchange so far. It's completely open to the public. We do sort of a Google Hangouts, I'm sorry, but every month, and we have this paper that we review. If you're interested, there's a link here. These slides will be up online in case, so you can actually get the link from my little link thing there. Other than that, I think we're kind of done. If you have questions or.
One more click.
Oh yeah. And Annika did the wonderful illustrations.
Yes, excellent. Thanks, John and Atif. I have so much ammunition now
Oh my
to
goodness.
use against developers. This is fantastic.
We can give you the real names internally.
All right, look out. So yeah, we have a lot of time for questions, which is good. Wait a minute, how did a developer submit this? Why not just delete all the flaky tests? Who let that developer in?
Well, I mean, if you talk to some of the teams who have flaky tests, first of all, it's impossible to get rid of it all. If you look at the 16% of tests that have ever exhibited flakiness, if we just deleted them all, I think some of our key apps would probably stop working. And some of them have very low levels of flakiness, which are fairly tolerable and don't often cause problems for the project. And ones that don't, we have active enforcement that moves them out of blocking releases. So we basically we ignore the results of tests that are flaky beyond a certain point until they get fixed, and bugs get open for developers to fix them and put them back into the test pool. So a certain level of flakiness is just a fact. It's a part of life, and we're willing to tolerate it if it's low enough, and if it's not, we just remove it from the blocking the releases, and then we do either delete the test or make it better. So.
I always find it interesting that developers can spend an entire week trying to get a different color to print out of their bash script, but when it comes to flaky tests, they say, just delete it. Mm-hmm. My own opinions, not of those of the speaker. How do you distinguish between flaky tests and real bugs due to concurrency, which will also pass-fail non-deterministically?
I'll let you take that one. Oh, come on. So I think the question really is that the bug is possibly in the concurrent code, and depending on the execution, the test that's testing it may pass sometimes, may fail sometimes. And I think the answer to that is, I don't think we distinguish. I mean, we still call that a flaky test.
Yes.
And then we pass it to the build cop, and then in the debugging process, they have to figure it out.
Yeah.
But I think from the signals that we have, until we start to categorize code as concurrent or not, until we use that as a signal, it's going to be very hard to distinguish.
Right now, it's really impossible from the outside, just observing the pass-fails, to be able to tell whether it's a bug in the code under test or the test.
Very good. Questions in the room? So let me read this one, and then I'll come over with the mic as you're answering. How much history on a test needed to be able to predict flakes? What if test has changed? Does it mean we need to gather more history first?
Yeah, so I think in the data that I showed you, there were several plots where I used a week worth of history. And of course, that most test targets tend to get affected during a week multiple times. So you have a reasonable set of data. And if the test case changes or the code changes, then you will see a change in flakiness. And we've started to measure that. In fact, Murat's project, I think, is doing that a lot. So that's probably true.
And at Google, I mean, we run all of our 3.5 million tests about every 20 minutes. So we get history pretty fast on new tests. So.
Hi, I'm Usman from BlaBlaCar. I just wanted to know about false negatives. How do you know that tests that are passing all the time are not flaky or broken because they always pass? And
Right.
can you use the data that you've been collecting to correlate the code that's changing a lot with flaky or bad tests that are passing all the time?
Right. So I like that question. Basically, what you're saying is, and I've been saying this all the time, when we define flakiness, the way we've defined flakiness is it goes from pass to fail, right? But a test might just pass all the time, but inside the code, when it's executing, it might be executing different paths, right? And if it's executing different paths, is that not flakiness, right? Unless it's designed to execute different paths. So that's been my definition of a flake.
And in fact, one of the interesting papers, journal papers we reviewed, they actually went and basically recorded all the program state as it was executing. And even without observing a change in the pass-fail, they observed changes in the code paths that were being taken, like the amount of code coverage and so forth, varied from run to run. And yes, you're right. That's in some definition of flaky tests. We're looking where the light is because we can see the pass-fail, but there's more under the covers that we haven't really looked at yet. It's harder to get at that because it's not reporting anything.
Right. And going to your second part of your question, once we start to correlate features of the code in the test code, then we might be able to go back to all the tests that were also passing all the time and see if they exhibit some of those features. And if they do, then we could flag them.
Very good. Any other in-room questions? Yep, hang on.
I have a question for the, you continuous integration testing, especially for the pre-commit testing or pre-merge testing, right? We need a quick turnaround for the test verdict against the patch from developer because everything is automated. We test pass, then we, carry +1, +2, right? If some case fail, we will -1. So then the patch will be gated. So at this stage, there is no room for flaky test. So I would like to know the Google's practice at pre-integration stage. How you identify the definitely you have the mechanism to identify the flaky test. But the more interesting thing I would like to know is what happened then, because everything is automated. If you, from my understanding, if you are confident that, okay, this is a flaky test, then this result will not block the patch, right?
Yeah.
So we need some mechanism there in CI system.
So I can talk about a couple of things. We've had some recent advancements in there, but the basic practice at Google is most teams block submission unless the pre-submit passes, and they indicate which projects they want to pre-submit against. So that's part of it. Yes, we do block submissions, just like you're talking about, and we do the same thing posting the results to the code review. There is a way in our system to indicate that a test is flaky. Developers opt in, and they say this test is flaky. If they say that, we rerun, if it fails, we rerun it up to 3 times and look for a pass. So then it will deflake itself sort of as part of the pre-submit. That's bad in the sense that if we allow tests to run up to 15 minutes. So if you have this test that has to get run 3 times, each time it takes 15 minutes to run before it reports a failure, you're delaying the developer by 45 minutes to get that result. So we've just started an effort. It's just launched a few weeks ago to actually exclude anything that's in our Flaky test database from running during pre-submits. We just exclude it. We don't run it during pre-submit at all. If a developer were to break that, we would catch it post-submit, but it doesn't block their submission, doesn't cause them a problem. So we actually keep statistics, and we exclude them from running on the pre-submit. Now, we do have a very fine-grained ability to control exactly which tests run during our pre-submits, and we run them all in parallel, so we get a result very quickly. And we also prioritize all of that work over anything for post-submit. So if a developer's waiting for our result, we give it our top priority in our back-end infrastructure. So it just goes out and farms and runs quickly and comes back. So between those different efforts, being able to deflake on the fly, being able to exclude the tests from running, and parallelizing massively the pre-submits, we give developers results pretty quickly on pre-submit. So.
Most developers are not so patient, right?
He said most developers are not so patient. No, they are not. That is true. And in fact, our 90th percentile latency for pre-submits is under 45 minutes generally. So you get back a result pretty quickly. And usually we spawn them off when you send the code out for review. We spawn them off, and then we post back to the review thread. Generally, the reviews take longer than 45 minutes, so we have a pretty good track record of posting the result before they need it. The rerun is fully automated. He's asked me if the rerun is fully automated when you say flaky. Yes, if you say this, if you mark the test as flaky, the rerun is completely automated, happens end to end up to 3 times, and then only if it fails 3 times in a row, it'll report back to the user, no, you failed, you actually broke it.
Hello, I'm Rahul Gupta from Oregon State University. So my question is something slightly different. In your graph about the number of authors who modified a file and how many of them caused failure, I saw a Goldilocks location at 2 authors. I mean, it's better than one single author modifying a file. So what's happening there, actually?
You mean the breakages go down when you have more than one author, right?
Yeah,
And
only until 2, but then it goes up again after that.
I mean, the breakages go up significantly so you have 3 authors. And I don't think we explored that. I think we have we guessed that when 2 authors are working on the same file, they most likely are better at collaborating with each other, right? Because they can send, and this is very specific to how Google does stuff, right? You have a single code base. If somebody is modifying a file, you can know when somebody modified the file. You can contact that person. Everything is open. So maybe they talk to each other, or they send email, they review each other's code, so breakages go down. It's almost like another review process.
So is it something like a pair programming or something, or is it more distant in time?
I think it's something to explore, but I wouldn't say directly pair programming. I don't think they're sitting together, but yeah, I mean, I think it's more of a code review.
So far, we've observed the astonishing result, but we haven't dug in to figure out exactly why.
Right.
And we'd like to know more.
Yes.
I just assumed it was the developer's intern came in, and that's the second author. He told him to fix all their bugs. Another question, a good question I saw up here. How can other companies leverage this research?
I'm happy to talk about the research with anybody else up to the extent that I can. I am a professor, so I will do anything for a free lunch.
Believe me, he wasn't free. No, but in all honestness, we really are publishing all this results in papers. We want to work with other companies and collaborate to share our ideas and our results. Contact Atif, contact me. Happy to collaborate with you, explain what we did, come and talk about it. We really want to get other companies to, at least if they can't share exactly the code that we have, at least share the ideas. And we really want to be open with our data sets and our ideas to the extent that we can be.
I'll read this one and come on over with the mic, but what priority do the teams place on fixing flaky tests? On fire or meh?
I'll take that one. So in terms of working practice at Google, every team decides for themselves how strictly to adhere to any process. They define what their processes are, and they define their adherence levels. I will say large groups, most of the large groups at Google that develop most of our main apps pay very close attention to flaky tests. They're all using the same work practice of removing flaky tests from blocking their builds and blocking their submissions. And they aggressively pursue developers to fix flakiness. And when your test is quarantined due to flakiness, your choices are to fix it or to delete it. I mean, it's pretty, I'd say most of the work practices are good, but again, there's always exceptions. There's 30,000 developers at Google broken into small teams. It's hard to say that all teams are doing it, but generally the work practices in that area are pretty good.
Hi, I'm Manisha here.
Oh, hi, Manisha.
Anisha, I'm from Red Hat. And so there was this slide predicting that a test will be a flake before running it. So all the parameters that are mentioned there, they relate to a UI test with Selenium WebDriver. So are the UI tests the only ones that you are terming as flaky ones, which we know that are the most prone to? Or you've seen the other ones, some relating to the API or the backend that have given this trend of being flaky?
I think, so UI tests are not the only ones that are flaky. We've observed that most of the time tests that depend on external resources, like if they're making some RPC calls or they're waiting for something, they tend to flake out more. Okay, and when it is during the day, right, when the test is running, those resources tend to be used more also, right? And this is one problem with the current approach where we run tests 10 times at night, right, to kind of figure out if there were flakes or not. And those resources that they're waiting for, they happen to be available at that time because they don't get used that much at night. So if we suddenly see that, okay, this test is passing.
You know what, we didn't do the statistical correlation between sort of test type, whether it's a unit test, system test, partly because we don't have good information about which of our test targets are, say, web tests, or we didn't divide the space in that way. I think it'd be interesting to know what those correlations are, but we have observed flakiness in absolutely every kind of test and absolutely all of our code base at some level. Okay, is it more in web tests than maybe it is in unit tests? Maybe in less than, I think yes. I think it's probably going to turn out to be true, although we haven't studied it, that integration tests and web tests tend to be more flaky than smaller, more isolated tests. But it would be great to show that from the data.
There has been some work, although I don't know if I can talk about it, where they were able to partition successfully into test types and then say that these are less likely to be flaky and these other ones are more likely to be flaky. But if you think about test cases that run for a long time, right, and require many, many more resources, let's say this one test depends on 5 services to be available at the same time, and it's going to run for 15 minutes. That's more likely to be flaky than a unit test that just calls a bunch of methods, right? So I think that result is lurking somewhere in the data.
All right, thanks. I have another question. You mentioned about the positive edge and negative edge. So I just want to know, how do you measure the number of edges? Like if I'm using Jenkins as my CI tool, I see that the number of builds passed, failed. So how do you measure the edges based on the amount of data that you had? Is there a tool or? No,
I just wrote a bunch of MapReduce to go through the test history, and then whenever it went from pass to fail, fail to pass, just start collecting all those.
But we did it at the test case level, which means you'd have to get out the XUnit XML files from the Jenkins invocation to go down to the next level and say, here are the 300 tests that I ran, and this one, here's the history of that test. Our system automatically breaks those down for us so we can see each individual test, its history individually, and you would have to start recording that data for you to be able to analyze it in the same way and find edges for individual tests to say that test is flaky, this test is not flaky. If you just look at the Jenkins top level display, you're going to see the whole build passed, the whole build failed, the whole build passed. There isn't any edges there really, right? You would have to go digging into the actual XUnit XML files and extract them. Jenkins lets you do it now. Some of the newer pipeline versions let you extract the XML and parse it right out of the box. You can do that. I'm sure there's also plugins that do it.
Yeah, we need to parse the data then for that.
You need to parse the XML.
It's there. Yeah.
Thank you.
I think we had time for one more question back here.
Hi, I have a fact to share. I'm Abhijit from MathWorks. So we also have a lot of Selenium, which are web UI based tests, and we were having a lot of flakiness. Out of our 100%, around 17 to 18% were flaky tests. So we decided to run a pilot where Selenium tends to be very flaky if it runs one particular test target or test file for a long time. So we kind of divided it such that none of the test targets take more than 5 or 6 minutes to run. And we found that our flakiness reduced to 5% out of 17%, which was one very good outcome of that pilot. I had a question for John. So with your new system that went live a few weeks ago, you said that flaky test, you do not run it for pre-submit. You run it with post-submit. So flaky tests do have importance. They tend to find regressions. So if it's after post-submit and there is an actual regression in that source code, you are kind of delaying that regression to be identified at a later process then.
Yes, we are, but we found in practice that developers would ignore the failure signal from a test that they knew to be flaky or that was marked as flaky. And in fact, our UI even will tell them it's flaky. So our UI for the test result says, your pre-submit failed because of test XYZ and it was flaky. And users, even if they broke that flaky test, they universally would ignore that signal and check in anyway. So I mean, it was just an acknowledgement of that behavior and saying, look, it's better to let them submit. And we actually now are also starting to explore on the other side auto rollback for test failures. So if a test failure happens, we roll back someone's CL automatically. We're starting to explore that in one of our groups. So that's our remedy to, oh, they checked it in and it was no good, we'll roll it back automatically for them. And I used to work at MathWorks, by the way.
All right, great. That was an excellent talk to end on and gives us a lot to think about at the dinner tonight. Thanks, Atif and John. Another round of applause.